Good afternoon, everybody. Thanks for joining. We appreciate you taking the time out of your day to join us for our presentation today on enhancing wind turbine performance analysis through lubrication. My name is Brad Prickett. I'll be your moderator for today. I've been with ExxonMobil for 22 years, 17 of those working with the wind industry in various capacities. Gearbox, inspections, oil analysis, and condition-based maintenance. With us today, we also have Bruce Hamilton from Navigant. Bruce, if you would introduce yourself, please.
Yes, hi. Thank you, Brad. This is Bruce Hamilton. I'm a director with Navigant. I'm based in Portland, Oregon. Navigant provides consulting services in support of the wind industry, both onshore and offshore wind, and related areas, including operations and maintenance, strategy, policy, market research. And among those, we have a O&M benchmarking service where we address issues such as condition-based maintenance and other O&M topics. So I'm here to talk about some of the results from some of the survey work we've done on that area.
Thanks very much. Thanks very much, Bruce. We also are joined by Bill Gillette of Logilube. Bill?
Hello all, this is Bill Gillette, and I am the founder and CEO of Logilube, and we are a 5-year-old company that has been built around condition-based monitoring of mission-critical equipment, and we're actually integrating an end-to-end ecosystem that involves Internet of Things sensors, big data analytics, and live dashboards, combined with the ability to corroborate the real-time data with laboratory analysis data. And our focus has been not only in wind, but also in oil and gas applications, as well as mining and mineral processing of mission-critical equipment.
Very good. Thanks, gentlemen. We appreciate you being with us today and taking time to share your knowledge. So what we'll discuss today is the state of the wind industry, just a short stint on that, along with what we're really here for today, which is best-in-class condition-based monitoring and how do we get there as companies out there. Finally, we'll talk about the next CBM frontier, which is lubrication as a service, and then we'll follow up with some questions. As far as the state of the wind industry, it's growing very quickly. Over the next decade, the U.S. wind market growth, it's going to range between 5 and 12 gigawatts installed per year, totaling around 76 gigawatts. And this will really be dominated, the installations will be dominated in Texas, the Midwest Plains, and mountains in the near term. But as we grow more and more, turbines are going to continue to get larger and be moved out into further spaces. So the market is going to spread widely. This wide spread of turbines, along with the big installations, is going to really drive having to be better at condition-based monitoring, as we don't have the necessary manpower to get to all the turbines in a timely manner. So what's pressuring today's wind sector? Really, it's two things. First is the phase down of the production tax credits, which I'm sure you're very familiar with. In 2019, we have a large construction bubble because of this 2019 phase down. Currently, there's about 97 gigawatts that are in operation, and 17 gigawatts are under construction just in this first quarter of 2019. So again, big growth and big installation there. The industry is also going to be entering a new post-warranty phase. By 2027, 87% of the U.S. wind fleets will enter post-warranty periods. So the turbines will not be covered by any manufacturer's warranties, and the O&M costs will shift directly to the owners and operators. This is going to really drive the importance of condition-based maintenance and condition-based monitoring to ensure the reliability of production and maximum, pardon me, and maximum output of the turbines. When you look on it as a whole, the production tax credits increasing and also the maintenance costs increasing, you're really driving the increase in LCOE, or levelized cost of energy. Currently today in 2019, we're operating at about 34.5 dollars per megawatt hour, with a maintenance cost around 13.7 megawatts per hour for O&M. And you can see when we look out into 2022, the maintenance stays about the same, maybe drops a little, but because of the production tax credits going away, you can see a real driver in the LCOE going up. So again, driving the importance of condition-based maintenance and condition-based monitoring so we can bring those costs down of operation as a whole and maximize production. So what does this mean? Operators need to evaluate their least variable costs, which what we're going to talk about today mostly is operations and maintenance. So from here, I'm going to hand it to Bruce Hamilton of Navigant to chat more through data analysis. Bruce, take it away.
Okay, yeah, thank you, Brad. As I mentioned, Navigant has a wind O&M benchmarking service. We call it GKS Wind, which stands for Generation Knowledge Service. And it's similar to other benchmarking products we have for fossil and hydro. What we do is we collect data from owners, both in cost, performance, staffing, and other areas such as failure rates and design data. And as part of that, we conduct a survey of a topic that's of mutual interest to the participants. And one of the topics that we have done recently is condition-based maintenance and predictive analytics. So I have some of the results of that survey to share with you today. Let's see, I'm going to ask, actually I have control, so I'm just changing to the first slide that shows a bunch of pie charts here. So one of the questions that we asked of the survey participants is of the various kinds of CBM data, how often, or I should say, how do you collect it? Do you collect it online, or do you collect it through some manual effort, or do you not collect it at all? And there are 4 different kinds of data that we asked that question about. The upper left pie chart there shows responses for vibration analysis, and you can see about 2/3 of the respondents say yes, we collected and it's online, and that really means it's collected by SCADA, so it's essentially continuous. Every 10 seconds would be a typical frequency. The next one, the upper right corner, is gearbox oil sampling, and you can see it's the exact opposite there, is that 100% of the people surveyed said, well, we collected but not online. So what that really means is grabbing oil samples at some frequency and then sending those samples to a lab for analysis. The lower left pie chart there is a mix of the two. Well, that's actually, it's similar to the first one, is that people generally collect grease sampling data online, but only half of them do that at all. So the other half just don't monitor that. And in the lower right pie is a mixed bag there. This is oil debris monitoring, and about half of the people said yes, we do collect that with online via SCADA. About 1/3, or actually about 1/3 do that. About half of it do it offline, and then 1 out of 6 or so said we don't even bother. So it's a mixed bag. It's certainly dependent on the technologies, and it's always a moving target as well. The general trend is that more and more people are bringing all types of data online. So that leads to several things, implications on what you do with it next. The next slide answers the question of how frequently do you collect data. And this is looking at two different types here. Vibration analysis is on the top pie, and the most common response to that is every 10 seconds or less. That's the SCADA collection, that 50%, the blue slice. And the other slices represent, less frequent data period collections. Some up to once or twice a year. And that's the most common response to the lower pie chart on the oil and grease analysis. 2/3 of the respondents said only semi-annually or annually, and you do it manually. It's not automated. So there's an opportunity there, as you might imagine. Okay, the next slide is the responses to a question that talks about what are the plans for IIoT, which stands for Industrial Internet of Things. And we're going to hear more about that from Bill Gillette later today. So this is the question of what do you do with the data? And there are various phases that companies go through as they become more accomplished and have more data to deal with, etc. So you can see there's 4 sort of levels here. The first level on the lower left is, we take the data from many places and we act on it. And 75% of the people said, yes, we do that. And that's fairly basic. It's been going on for years. The next level up talks about, do you build statistical tools and use those tools to identify outliers of data and then analyze it? And then only 1/3 of the companies said, yes, we do that. So that's, a little drop off from the first one. The next one up takes it to the next step of building machine learning models based on the failures and using the models to actually predict future failures. And 1/3 of the companies said, yes, we do that. And this, by the way, means they could be either doing it in-house or through a third-party vendor. And there are many third-party vendors that are in this business. And then the fourth and final level, which you can see actually nobody has claimed to have reached yet, is to have a completely integrated, diverse system for collecting all data, various unstructured pieces of data from maintenance logs, cameras, and other places, and to have a fully integrated system. And these are all, you might consider levels of artificial intelligence, which is the buzzword now, and there are many other buzzwords, I'm sure. But this is where the industry is headed. And in all cases, even though the companies didn't actually currently do that, they all had goals of getting to the fourth level. So that's it's kind of a quick overview of the survey, some of the survey questions, and I think it's a good indicator of where the industry is headed. So I'd like to turn it back to Brad.
Thanks, Bruce. Really appreciate the information. As you can see, data analysis is very important in operations and maintenance, and we all want to strive to get to the point where we integrate the diverse unstructured data, essentially the AI point, so that we can drive forward with the best production from our turbines. Moving forward, let's look at how lubrication can play a role within the operation and maintenance and condition-based monitoring and maintenance. Ultimately, lubrication can help identify real-time equipment operating conditions so that you can really see problems before they happen. And that's through oil analysis, as the majority of you are doing, but maybe not in a real-time basis that we'll hear a little bit more from Bill Gillette on in a few minutes. Really, lubrication plays 2 important roles. First, it properly protects the equipment from premature wear. As you can see from the diagram, lubrication touches many of the critical parts in the turbine so that uptime can be maximized gearboxes, pitch gears, open gears, yaw gears. All these need to be kept operating at max performance so that we can gain the most productivity out of the turbine itself. But secondly, since the lubrication touches all of these important points, it carries a lot of great information once you start to analyze and look at the data. So really, we want to use lubrication as that key to look at equipment condition, as it unlocks a wealth of information into the turbine and the rotating parts themselves. We want to look at the lubricant condition itself. How long can we go between oil change intervals? How long can we go between greasing intervals? That all is key in reducing LCOE. And then finally, contamination. What type of particles are coming into the lubricant itself, and can we identify where those contaminants are coming from, whether it be maybe an outside source such as dirt, or it may be from an internal source such as wear from the gearbox or the bearing. And again, all of these things lead up to condition-based monitoring and maintenance, and ultimately drive your uptime and production to lower your LCOE costs. So now we've learned a little bit about lubrication's role. We're going to hand it off to Bill Gillette to talk a little bit more about how we might be able to use real-time data tied to lubrication to make condition-based maintenance and monitoring decisions. Bill?
Brad, thanks for the introduction, and I'd like to welcome all of you to this next 20-minute presentation on our technology that we've developed. Actually, I'm going to, let's see here, I'm going to move some slides forward here. All right, so here we go. So LodgeLube is a almost 6-year-old company that was developed and formed in the northern Front Range of Colorado, and we are a small firm that is made up of a series of engineers from mechanical, electrical, and data scientists. What I'm about to share with you is a technology that we developed called Smart Gear, which was actually, this project is based around a Department of Energy CRADA project that was hosted at the National Wind Technology Center, NREL's Wind Technology Center, just south of Boulder. So in this presentation, I'm going to, first of all, I'm going to lay out a description of the ecosystem, as we call it, an end-to-end solution of the hardware, the software, the services, etc. And then at the tail end, I'll walk through some examples of findings from this CRADA project. First and foremost, it was based on monitoring the condition health of the lubricant and also the gearbox of the wind turbine. This was actually fitted to a GE 1.5 megawatt turbine, and as you can see in this first slide, there's an orange outline around the actual what we call it the smart oil or smart gear device, and it's a small, maybe the size of a shoebox piece of hardware that contains within it an edge processor, essentially a hardened computer or CPU that does the edge processing, air quote around edge. In that the sensor is a suite of sensors, some of which are contained inside of the device, and many are external to the device. But all the various sensor data is then processed in real time, quote unquote, at the edge, in order to provide real-time data that can then be correlated with the physical oil samples that are pulled on an interval. This outline on this first slide illustrates the in-service sensor suite, and I'll just list off the various ones that were used in this project. first of all, we're measuring viscosity, and in this case, the gearbox has a 320 ISO 320 gear oil. Obviously, oil temperatures and pressure. We also measure the dielectric constant, the ability of the fluid to actually carry a charge. And from the dielectric constant, we can infer the state of the additive levels, as well as the presence of water, whether it's relative humidity that's saturated or free water. And then lastly, the last sub-bullet is foam detection. Because we have the ability to also measure small particles, we have the ability to discern between a dirt particle, a wear particle, as well as a bubble, an air bubble that could be caused from the mechanical churning within this gearbox in the event that the defoamant agent or the additive within the oil add pack has been depleted. So bottom line from this slide, 30-second reporting interval, and it's important to note that the 30 seconds is actually, what it's not is we're not measuring the data and reporting it at the top and the bottom of the minute, but we're actually taking 30 seconds worth of data, a large data set, and applying some data analytics to that and some noise detection and filtering to actually come up with a representative sample, data sample that represents that 30-second block of data. Again, this is in situ IoT or Internet of Things sensors. We're not a sensor company, but we do apply off-the-shelf, best available technology, and then do edge processing. With that, I'm going to move to the next slide. And we're now highlighting another set of external sensors where we're measuring wear particles, and these wear particles defined as very small down to 4 micron up through 21 micron, and they would be the typical example of the wear particles might be the metal particles that are being shed from the gear lobes as they have sliding wear between the gears, as well as the bearing surfaces, the raceways, and so on. Also have the ability to input debris particles or much larger particles, both ferrous and non-ferrous, 45 micron and larger. In this project, we did not incorporate vibration, but vibration signals could also be input from if we were to add accelerometers. And of course, additional sensors such as load, torque, RPM, SCADA data could also be integrated and processed right there at the edge processor, so that all the data inputs having a very particular timestamp, so now you can start to analyze the data based on a very common time imprint. Again, this is local edge processed, and the data is then every 30 seconds it is uphauled to a cloud via a wireless cellular connection. The site in Boulder had very good wireless capabilities, but in the event that we were deployed in a more remote area, we would certainly use a satellite modem. Again, the bottom line is the output of this edge processing is actionable information versus raw data. I'm going to move to the next slide and actually highlight how we move the packets of data. As previously stated, it is a wireless data transmission. Because we're edge processing, the actual data load or the packet size for each of those transmissions is actually quite small. In fact, to give you an example, if you were to take your smartphones and take 5 or 6 pictures with your smartphone and send those pictures as maybe a text message attachment, that would be the total packet size for an entire month's worth of data coming out of the system per asset. So as illustrated in the outline, The data coming from the edge processor, first of all, it's encrypted. You can see it's on a 30-second interval, goes through a gateway that actually manages the packets, the loading, the scheduling, so you don't have collisions. Also outputs through a fairly sophisticated modem, which has the ability to optimize which CDMA or GSM network might be strongest and available, and it then uploads the data to a remote app server for further processing. Once the data is in the server, it can then be exported through an API to the client's maybe a Pi historian if they're using OSIsoft or some other historian. The data could also be with macro routines sent to the client via a CSV file. Many ways to actually get the data into the hands of the client. And next slide. And I'll give you an example of some of the findings from this NREL project. This graph and the corresponding dial gauge illustrates a cleanliness, a particle cleanliness. We've got the ability to output the ISO code, the 4406 ISO code, and you can see here the 4 different colors that range from 4 micron to 21 micron. The historical plot down below here just gives a snapshot of a couple of hours worth of data, and you can see as there's actually, I'll have some more details further in the presentation of some actual events that we captured. But bottom line, it's the ISO 4406 cleanliness code. It's the source of the data is actually a laser-based sensor, and it is also ferrous, non-ferrous, and this is all live data that would be able to be viewed by the client. Next slide shows an example of a couple-hour window or history as we put this turbine through a series of forced emergency braking stops. So the turbine came up to RPM, and we put the brakes on and brought the rotation to a dead stop. And you can see here in the highlighted outline series of the graph where we actually induced large particle hits that could then be analyzed further on a time basis, as well as take samples out, as we did. We took physical oil samples post the e-brake event, and actually in a laboratory we were able to determine or corroborate the real-time data. So not only were we able to corroborate in the counts, but also to determine from an elemental analysis what the makeup of the particle was. Was it copper or bronze or iron coming from either the bearings, the raceways, or even the gear lobes as they were put under a tremendous shock and wear during the e-stop event. Next slide. I've mentioned several times how we corroborate the real-time data with laboratory analysis data, and you can see in this outlined portion of the slide where there is a series of oil sample bottles. You'll notice 3. There would be 2 that are classic 125 milliliter or 4 ounce, and then the one on the right would be a larger half liter or 500 milliliter bottle. And because of the fact that this application in a wind turbine is quite remote, and the mechanics or staff are up tower every month, they might be, as Bruce indicated, I think the average industry visit to the tower for sampling might be every 6 months. So since the oil that's contained in these bottles is actually the smoking gun evidence with proof of some of the events, we want to be able to store more than one bottle's worth of a sample oil. The larger bottle is actually was predicated based on the Flender test, or the Flender foam test, which requires a much larger oil sample volume. So again, with the edge processor running many simultaneous calculations and processes, if there was a foam detected, this larger sample bottle will be filled on an exception basis versus a scheduled machine time basis, and then the correspondingly a notification will be sent to a mechanic or a staff to actually go collect that bottle and verify in a laboratory, pulling the Flender test to verify whether the foam is actually depleted. And you can see as it processes through from left to right, the samples go off to a third-party laboratory. The data is then married up with the real-time data. And since we have timestamps for both real-time and the physical sample, you can go back and look at the history of the real-time data to see what led up to the event that possibly triggered the exception sample. Next slide. This slide is your classic, to all the reliability engineers on the webinar, this is a classic PF interval chart. But the point I want to raise in this diagram is on the lower part of the graph, where you'll see a series of oil sample bottles, and at about halfway through, you'll see a red bottle, which is indicative of an exception sample that was pulled based on some threshold or condensing limit that the algorithm indicated there was a problem. Therefore, the bottle was filled, notifications were sent, the bottle was collected, the sample was analyzed, and the corrective action was taken way before the system actually created through a catastrophic failure. Next. And speaking of notifications, this is just a collection of the typical oil sample events and machine event type of notifications that are sent either via SMS, text messaging, or email. And one of the last slides in the ecosystem is on the far right, and that is the output, whether the output is can be referenced via web-enabled dashboards, mobile smartphones. The data can be used for diagnostics, also marrying up the data from the laboratory versus the real-time data. Again, it's the combination of real-time online data corroborated with offline oil lab analysis data. At the end, it's providing actionable information for the mechanics and the operators to take action. And here you go. Here, this next slide is here's a picture of the NREL facility in South Boulder. There are about 8 different turbines there. The one that's circled is the GE 1.5 megawatt gearbox. It's a Winergy gearbox from Siemens, and this was commissioned back in February of 18 and ran for just over a year. Next slide is really kind of a results of the project. We went through a series of, as I mentioned, e-stops or braking actuations, and we were able to have a direct correlation between the particles, small wear particles that were caused by the sudden shock to the gear train system, as the system went from about 18 RPMs down to 0 RPMs in about 6 seconds. The protocol for this testing was done in concert between the gearbox team at NREL as well as the Winergy folks in the U.S. office in Chicago. So the bottom line results were an absolute clear relationship between these e-stop events and wear particle generation. And it's the group's position that with more data, consistent data from a larger data set, the goal is to be able to determine the remaining useful life, or the RUL, of these various gearboxes, tying together many different events, shock events, loading events, dynamic torque events, both positive torque and negative torque, throughout the life of these very mission-critical pieces of equipment. And with that, I'll hand this back over to Brad.
Very good. Thanks, Bill. Really appreciate the information on Modulube. It's a great step toward more real-time data. So just some concluding thoughts. As we went through the presentation, on Bruce's side, you saw that many of us, or all of us, do some type of oil analysis, but it's on a longer basis, maybe twice a year, maybe once a year. So the data really isn't fresh and able to be used in a timely manner. So as we look at lubrication as an effective tool, and we combine that with technologies such as Logilube, we can get more real-time data and make more effective decisions, which ultimately, again, reaches the goal of reducing LCOE and maximizing the turbine uptime and productivity, along with profitability for our companies. So again, I want to thank everybody for joining us today. We really appreciate you taking time out of your day to do so. We do have a couple audience questions that I think we can address at this time. So the first question, let me scroll a little farther here. So the first question is, what's the difference between Edge and a conventional data logger? Bill, I think that one goes to you.
Absolutely. Very simply, an edge processor or edge computer actually does the computations of the input data right there on the edge of the network. And in this case, the edge would be at the device, or for the purposes of the presentation, it was at the gearbox in the nacelle on the tower. And so the data, the just megabytes worth of data is then processed in real time right there, so that you don't have to uphaul big loads of data up through a wireless transmission, or I mean, you wouldn't even need the VPN or a hardwire connection, because the data packets are so small. Once you've processed the data, you can then determine, is it important? Does it fall outside of the threshold? Does it need immediate action? So it's and a data logger, of course, is merely grabbing the raw data and aggregating it and getting it ready to send up to a server via probably SCADA.
Very good. Thanks, Bill. Appreciate that. A second question we have, and this would be for you, Bruce. Based on the research from Navigant, are companies more likely to attempt intelligent condition monitoring on their own, or will they rely on third-party providers?
Okay, yeah, thanks, Brad. Good question. And I think with many questions like this, the answer is it depends. And it depends on the size and the sophistication and the appetite of the company, the owner. There are some companies, mainly the larger ones, that are attempting to do this kind of work in-house. There are the smaller you get, the less ability and appetite you have for this kind of thing, and so there are people who rely on third party. So I would say right now there's room for both, and both are growing. So that's a quick answer for that one.
Very good. Another question we have, can the gearbox monitoring displayed by LogiLube be applied to large industrial gearboxes as well? Would there be any significant changes needed in the system? So Bill, back to you.
Yeah, it's great. Thanks, listener, for that question. Excellent question, by the way, and there is a direct parallel and correlation between let's say, a wind turbine gearbox that we just referenced in the presentation, and let's say a gearbox used in an industrial setting at let's say possibly at a mineral processing site on a copper, or iron ore, gold ore, where you might be taking 3 to 6,000 horsepower, electric horsepower, to actually drive a pinion gear to rotate a grinding mill. And so there would be a multi-stage gearbox that actually takes the input RPM and reduces it down to 20, 30 RPM to drive the pinion. So since you have a flooded gearbox, a big gear train, many gears, you're still concerned about the quality of the oil, the condition of the oil, the viscosity, the water contamination, particle contamination, etc. Given that the duty cycle is continuous, typically 24/7, all year long, with values ranging from, let's say, $10,000 an hour downtime to $250,000 an hour downtime. So this gearbox and the gear health becomes very critical to the operation. So the smart gear system is directly translated between this wind turbine application and industrial gear turbine or gearbox applications as well.
Very good. Thanks, Bill, for the thorough explanation there. We do have one more question. What are the challenges for wind industry expansion? Bruce, over to you.
Yeah, thanks again, Brad. Another great question. Yeah, and so there are some challenges. Although right now we are in a boom time. We're approaching a record year. We're forecasting actually 2020 to be a record year, and then near the 12 gigawatt range, and then it'll drop off from that point, and that's due to the loss of the PTC. And that's certainly a challenge, as it boils down to is competitiveness of wind versus its main competitors, which are solar and natural gas, both of which are also dropping in price, in cost. So some of the things that affect costs are the availability of good sites, and that's a challenge in that they are becoming somewhat more scarce as the good sites are being used up, and so that leads you to develop plants in more remote areas, and that leads to transmission constraints. And so that's an area that's of keen interest. How do you overcome the transmission constraints and minimize curtailment? Also leads you to other parts of the country where you haven't typically seen wind power, such as the southeast and other remote areas. And those challenges are being met by the advancement of technology, with higher towers and larger blades that allow you to build wind plants in lower wind speed areas. So that's how those challenges are being overcome. I think the question also had referred to offshore wind, which has another whole set of challenges. And that's mostly a policy-driven business. And fortunately, the good news is that the policies are finally getting to the point where it's driving demand, to the point where the supply chain is starting to be developed here in the U.S. And that's the biggest challenge for offshore, is that many of the supply chain components are not built in this country. The major parts of the turbine, as well as infrastructure items such as vessels. So that, of course, adds to cost as well. So that's the challenge on the offshore side.
Great, Bruce. Appreciate the thoughts there on the challenges for the wind industry and growth. Looks like we have one more. How closely do you work with wind operators when it comes to assessing oil samples? I'll start that one with Bill, and then I'll end up with that one as well. Bill, do you want to give a couple of thoughts there from the LogiLoop side?
Sure, exactly. And I'll reference from some past experience. Typically, we work very closely with the reliability engineering team at the client site. And since we have the ability to illustrate real-time data, 30-second interval data, corroborated with the physical oil sample data, upon commissioning, we actually work with the reliability engineering team to determine what are the condemning limits, what are the warning limits, both high and low. Oftentimes, those values are either determined by the lube oil supplier. Given the case of, let's say, viscosity, there would be very discrete values of what's an upper threshold and a lower threshold for movement on viscosity. Same with water contamination. There may be, due to condemning limits, maybe coming from the OEM, and this could be a warranty issue. Those values would be driven by the OEM. And so when we go through a complete commissioning process with the operator to determine what these values are, then not only the dashboard, the live dashboard data is set with these thresholds, but also, and just as importantly, with the third-party labs. Remember, we're not a lab company, but we would work with the client's lab, and the data is actually pushed via an API from the lab to the dashboard. But those upper and lower threshold limits and condemning limits would be then fed into the lab's software, so that the requisite alarms are built into the system. So short answers or long answers to the question, but the short answer is we work very, very closely with the operator in not only determining the values in the used oil analysis, but also in interpreting the data afterwards.
Very good. Thanks for the comments there. As we saw from Bruce's piece of the presentation, as far as oil analysis goes, really most of that currently is going to a physical lab, and then our operators are receiving that data back. From the mobile side, ExxonMobil side, there's really a twofold piece here. The first piece is that we work closely with the OEMs and manufacturers of the specific component to put proper data limits around the oil analysis results, as far as what wear they may like to see in relation to that component. The second piece of that is our mobile serve brand, where our engineers work directly with the customer to interpret the data that they receive back from the mobile serve lubricant analysis lab, and from there create plans on what maintenance may need to take place. Ultimately, again, looking for that maximum uptime. And further to that, if a site has a LogiLube, then we'll work directly with LogiLube as well through MobileServe to combine that data and provide even further service to the operators. So with that, it appears that we do not have any further questions. I'll wait one more minute if you'd like to submit one in the chat on the audience questions. Wait for just a minute. Okay, it appears no further questions. So again, I want to say thank you for your time and participation. We really appreciate you taking time out of your day to join us. If you would like to send a question to any of the presenters, you can see on the screen now all of our contact information, and we'll be happy to chat with you or get back via email, however you may want to contact us. So again, thanks for your participation, and we appreciate the time. Have a great day.